So we are discussing about the transactinides, and also today we'll be covering chemistry of some of the transactinides, the early transactinide elements like element number 104, 105 and 106. So the chemistry of transactinides, mostly there are two types of chemistry. One is the gas phase chemistry and another is the solution phase chemistry. The gas phase chemistry is relatively easier because of the very fast transport in case of the gaseous molecules. But in the solution phase chemistry, there will be some sort of a separation is required, which I have discussed in the previous lecture, how the atom at a time chemistry is done. So the chemistry in the solution phase mostly involves partitioning type of experiments, that is ion exchange, chromatography or solvent extraction. So we'll come details of those chemical aspects in the aqueous phase as well as the gas phase. While studying the gas phase chemistry, mostly the volatility of the halides or the oxyhalides is studied. Now these transactinide elements, they are part of the fourth transition series, and the chemistry of these transactinides in the gas phase is always compared with the other elements in the second or third transition series. So for example, if we are studying the gas phase chemistry of rutherfordium, which is element 104, so we need to study the volatility of rutherfordium chloro compounds or the bromo compounds, that is RFCl4, which is a volatile compound, and we compare that with the transition elements like zirconium chloride or hafnium chloride, so that is HFCl4 or ZrCl4. Similar comparison also can be done with the bromide complexes like the ZrBr4 and HFBr4 compounds. And the same way, we can also compare the volatility of element 105 chlorides or bromides or oxychlorides, that is the dubnium compounds, with that of the tantalum as well as the niobium compounds. So in this slide, we compare the volatility of these chloro, bromo or the oxychloro compounds. The left figure, it is the zirconium chloride and zirconium bromide, and their volatility is compared with that of the hafnium chloro complex as well as the hafnium bromo complex, that is HFCl4 and HFBr4 complexes. As you can see, the hafnium chloro and the bromo complexes are relatively more volatile as compared to that of the zirconium bromo complexes, as shown here. The hafnium chloro and hafnium bromo complexes following the same pattern, and their volatility is higher than that of the zirconium chloro and the bromo compounds. Now coming to the tantalum and niobium compounds, you can see that the chloro compounds of tantalum and niobium, they are more or less same, shown here. On the other hand, the bromo compounds are having much lower volatility, shown in the profiles given here. This is for the tantalum bromide and also the niobium bromide compound. Now the oxychlorides, again you have the tantalum oxychloride is having much lower volatility than that of the niobium oxychloride, which is having more or less similar volatility that of the niobium bromide. So in a similar manner, experiments can be done for the rutherfordium chloro complexes and also to form their oxychloro complexes as given by this equation by reacting with oxygen, and this can be compared with that of the zirconium as well as hafnium complexes. Now how this gas chemistry studies are carried out for the transactinides. The experimental method is rather simple. There are two types of experimentation is done. One is the thermochromatography and other one is the isothermal gas chromatography. The early studies, the Dubna lab in Russia, they used the thermochromatography column, which is directly connected to the recoil chamber. So the gas phase chemistry was nothing but a measure of the volatility of the compound. This method was very simple and also very fast method. So in this case, the detection was done by fission track detectors. So basically, the thermochromatography as a function of the length of this column which is there. Basically, you have a column, and when these volatile compounds are passed from one end, so the temperature along this column is changed. Actually, it goes from starting from 450 degrees to room temperature in this way, going down, and then depending on the volatility of the compound, they will be deposited, and in this inside surface of this tube, the fission track detectors are implanted, and by taking out the fission track detectors, can monitor where exactly the compounds are deposited. However, there are some disadvantages, even though this method is so simple. But the real-time detection of the nuclear decay of the transactinides as well as their half-life determination, and it was not possible. So subsequently, this experimentation involved something called the isothermal gas chromatography, which is used by this online gas chromatography apparatus or OLGA. And this case, the reaction products are carried by graphite aerosol and are trapped in the reaction oven where the gases such as hydrogen bromide, hydrogen chloride, chlorine, oxygen, or SOCl2, etc. are passed and are allowed to react with the transactinide atoms which are coming from the reaction chamber where the heavy ion reaction is taking place, and the reaction is done at around 900 to 1000 degrees Celsius. And after that, these transactinide compounds are coming to be collected at this detector system, which is called the ROMA, which is nothing but a rotating type of detector system, and which is also going to be counted by alpha spectrometry by a set of PIPS detectors. Now, in this case, the ROMA actually does the counting using the PIPS detector, and the retention time of the volatile compounds, in this case, the chloro, bromo, or oxychloro complexes of the transactinide, is determined by using the half-life of the radionuclide as a clock and the temperature at which the 50% plateau yield is observed, that is the T50, the retention time is termed as the half-life. So that is how the half-life can be determined of these gaseous products of the transactinides. Now coming to the aqueous chemistry experiments, there are several sophisticated instruments are used for this. This instrument has been designed in a special way so that these transactinide compounds can be separated and also can be detected using a special type detecting system. The first of such instrument is called the automated rapid chemistry apparatus or ARCA. Major part of the aqueous chemistry studies which are reported in the literature, they use ARCA, which is having basically several miniaturized columns. The columns have 8 millimeter height and 1.8 millimeter internal diameter, and the typical cycle time is around 40 to 90 seconds, and there will be around 20 such columns in a magazine. This ARCA system I can show in a little more clear view. Now the schematic I can show here, where I have the front view as well as the side view. As I was showing, this is the magazine actually. This one is the magazine where you have these columns embedded into the magazine. The column has around 8 mm height and a very small column which is around 1.8 millimeter as the internal diameter. And this is the front view of the magazine here, and this helium gas jet potassium chloride gasette system is coming here and it is forming a solution, and the solution is passing through this. It comes to alternatively to these two magazines which are having the columns. It is passing through that, and separately there will be the element will be coming, and the element will be passing through the column. That is how this effluent will be coming and will be collected onto this planchette, which will be dried and counted by either alpha or gamma spectrometry. Alpha spectrometry for the transactinide, and gamma spectrometry for the homologs, which are like zirconium or hafnium isotopes, which are short-lived, and those are used sometimes to monitor the chemistry in an online method, the way the transactinide experiment is done. In such case, the zirconium, hafnium online data can be compared with the Rutherfordium online data. In a similar manner, offline experiments are also done, taking relatively more stable compounds of zirconium and hafnium or niobium and tantalum, or in case of Seaborgium experiments, it is molybdenum and tungsten isotopes are used. And in this case, mostly you have this different microcolumns in the ARCA system. Subsequently, this has been also upgraded by the Japanese researchers to be called as automated ion exchange separation apparatus coupled with the detection system for alpha spectroscopy, which is called as IDA. Now, another type of instrument which is used for this fast separation for the transactinide is called the SISAC, or this is the short-lived isotope studies by the Acouphey technique. Acouphey is a very fast extraction. In this case, extraction is by solvent extraction. So Acouphey is a solvent extraction system where automatically after equilibration of the organic and the aqueous phase, a part of this mixture will be pipetted out and it will be centrifuged and separated. All these things in a very, very short time period, such that these experiments can be carried out in several minutes or so in case of the Acouphey system. And some cases it can be done even faster to go to the seconds level, and there is used for the transactinide separation chemistry studies. And this SISAC has been developed by the Swedish research groups, and they have used, this is a system is given where you have actually several extraction as well as centrifuge methods are there. This setup is there, and you have the aqueous phase is going into this, and the gas phase also is going inside this, and they will be mixed here, and then the degassing can be done. Then it will go into the extraction as well as the centrifuge stays here, where the organic phase will be inserted into this system. So fast extraction and centrifuge is done, then aqueous phase will be taken out of the system, and the organic phase will be going this way, and it will be countered by the liquid scintillation counter. So this is very, very fast system, and several experiments have been carried out by this SISAC setup, which I will be discussing for some of the transactinides. Now coming to the individual transactinides, first let us go to the Rutherfordium or the element 104. We discussed first the aqueous chemistry of Rutherfordium. The major complexes, as we know, for the actinides and the transactinides are the hydrolyzed species in case of the aqueous phases. So therefore the acidity of the aqueous phase needs to be controlled. If it is normal pH conditions, then we are having the hydrolyzed species. So for the group 4 elements like Rutherfordium and its homologs like zirconium and hafnium, we have that this at pH greater than 6, we get the pentra-hydroxy anionic species, which is like this, MH2O and then OH 5 minus, this type of species, and we can have X number of H2O. So this type of species will be formed for the tetravalent metal ions like Rutherfordium as well as zirconium and hafnium. The hydrated species can undergo also complexation. Here I have shown how this hydrated species can form a complex with complexing agent like HX, where X minus is the anionic species which is forming a complex. So the species, if it is not having hydroxide species, then it can form like MxH2O 7 3 plus. That means the tetravalent ion is not having any hydroxo complex. In that case, it will form complexes like this, and it will continue to form the complexes till it has completely anionic complexes like MX6 2 minus. So example of this type of complexation is MF6 2 minus. So that is the fluoride complexes of zirconium, hafnium or rutherfordium. This forms species like MF6 2 minus, and the hydrolyzed species also can form complexes like I have mentioned here. You can have a precipitated form of these tetrahydroxy complexes of the tetravalent metal ions like zirconium, hafnium or rutherfordium, and this precipitate can form complexes with HX giving MOHX plus H2O, and subsequent complexation can take place to give MX4 type of species. And the MX4 also can complex with another HX to give MX5 minus, and subsequently with another HX to give MX6 2 minus, giving species like this as mentioned. Now coming to the aqueous chemistry of rutherfordium, we know that rutherfordium is a member of the fourth group as shown here. So it has a oxidation state of +4, and it has the ionic size. Hafnium is having 0.71 angstrom, rutherfordium 0.78 angstrom, and thorium 0.94 angstrom. Why I mentioned thorium here? Because thorium is an actinide series as mentioned here, and this is called as the pseudo homologue of rutherfordium. So the transition elements in the group 4 like titanium and zirconium, they are considered as the homologue of rutherfordium, and thorium 4 plus is considered as the pseudo homologue of rutherfordium. Now based on this ionic size, this is for the hexa coordination, the fluoride complexation will follow the ionic potential. So that is hafnium is greater than that of rutherfordium, is greater than that of thorium. Fluoride is a hard ligand, it can form a stronger interaction with the hard cations like hafnium, zirconium, and to some extent rutherfordium. And so rutherfordium forms anionic complexes like RF F6 2 minus, and it also prefers to form complexes with the chloride ion based on the hard soft acid base principle because it is relatively softer as compared to hafnium. So I've shown a figure here where the experiments have been carried out by the ARCA system, and the system contains a small quantity of hydrogen fluoride, that is 3 into 10 to the power minus 3 molar hydrogen fluoride, and also varying concentration of nitrate, that is the nitric acid concentration is varying, and the Kd values are determined, and you can see here that the species which is formed is RF6 2 minus, or for zirconium and hafnium it is MF6 2 minus, where M is either zirconium or hafnium. And with increasing nitrate concentration, you find that this Kd values is decreasing with a negative slope of -2, suggesting that the extracted species is indeed MF6 2 minus. This type of species are formed, and with increasing nitrate ion concentration, this Kd value is becoming less and less. And same type of species was also seen in case of rutherfordium. You have -2 species slope here. So that suggests that the extracted species is MF6 2 minus in this case. And the chemistry of rutherfordium as shown here is similar to that of zirconium and hafnium. Also ion exchange studies have been carried out for rutherfordium, where the study has been carried out with varying concentration of hydrofluoric acid, that is HF, and also 0.1 molar nitric acid has been taken in these experiments, that is a mixture of nitric acid and hydrofluoric acid, and the rutherfordium was transported using the potassium chloride helium gas jet transport system. And on the cation exchange regime, you can see that at the hydrofluoric acid concentration of around 10 to the power -3 or lower, you can find out these Kd values are becoming very, very large. So that means the anionic species are not formed and the cationic complexes, they are jorbed onto the cation exchange regime. But if you increase the HF concentration beyond 10 to the power minus 3, you find that these Kd values are dropping. And as shown here, the comparison has been done between this uptake of zirconium, hafnium, thorium and rutherfordium using this cation exchange column. Zirconium, hafnium and thorium data are generated by offline method, whereas the rutherfordium data was generated by an online method, which is very obvious. And you see here that the thorium offline data is actually entirely different than what has been seen for the zirconium and hafnium. Zirconium, hafnium is following a pattern here, and rutherfordium is in between. Rutherfordium is falling actually in between. That means it is, at some experiments, it may be falling close to that of the zirconium and hafnium data, and some other cases it is lying in between that of thorium as well as zirconium and hafnium. So get some more clarification, the ion exchange studies were carried out again with offline, and in this case some online experiments also were carried out using hafnium. So rutherfordium experiments are always carried out online, but the hafnium data presented here, the left hand side figure, is both offline as well as online. And you can see that this hafnium online data, which is the solid circle, and the hafnium offline data, which is the purple line shown here, they are more or less matching. And you have the thorium offline data, which is lying here, which is matching in this case surprisingly with the rutherfordium online data. You see these triangles are the rutherfordium online data. So for the cation exchange column experiments, the thorium data is matching with that of the rutherfordium online data. And this experiment was repeated using an anion exchange regime. So the experimental condition is same, but you have a reverse pattern here in case of the cation exchange regime. Initially the Kd value was low, that is at low concentration of HF where the fluoride complexation was not there. Those cases you have the cationic species and we are jobbed onto the columns. And in case of the anion exchange regime, you find that lower concentration of HF because anionic complexes are not formed, so the uptake onto the anion exchange regime is not there. You find the very low Kd values. But at higher concentration of HF, you find that the anionic species are formed, and then you find that the Kd values are going up. But what is interesting in this case is that though the hafnium offline as well as the hafnium online data, they suggest some increase actually with increasing the HF concentration, and also which is matching with the zirconium offline data, which is shown here. The thorium data actually is showing no change at all. That means thorium is not forming a fluoride complex, and surprisingly, rutherfordium also gave the data which are matching with the thorium data points. So in the cation exchange as well as the anion exchange experiments with the rutherfordium, zirconium, hafnium and thorium, the conclusion was that rutherfordium and thorium data points were matching with both the type of regime. Now coming to the CISAT experiments with element 104, that is rutherfordium. In this case, the solvent extraction experiments were carried out with the group 4 elements using trioctyl amine, which is a tertiary amine in xylene, and the experiment was done from the sulfuric acid medium. And as shown here, the data of zirconium, hafnium and rutherfordium all in the tetravalent or the +4 oxidation states. The distribution ratio values, they increase as a function of the TOA, that is a trioctyl amine concentration. And you find the straight line plots in these log-logged plots, and the slope value of these lines are around 1.4 and which is more or less consistent for all the three types of metal ion, suggesting that the mixed type of extracted species are formed. That is, this extracted species is having either one or two amines. So that is how you get a mixed species, and the slope value is around 1.4. So this HISAC experiment also shows that the pattern of zirconium, hafnium and rutherfordium, if we see that the zirconium extraction is the highest and followed by the hafnium extraction, and which is followed by the rutherfordium extraction. But you find that this rutherfordium extraction is comparatively lower than that of hafnium extraction. Now I come to the element number 105, which is the dubnium, and I mentioned here the aqueous chemistry of dubnium. Dubnium, again, it is has the homologues vanadium, niobium and tantalum. It has a pseudo homologue is the protactinium. It is a member of the fifth group as mentioned. So we have niobium, tantalum and dubnium, which are forming the same group, and the first experiment is carried out in this case was the observed on the glass surface from the HCl and nitric acid solutions, which is again a characteristic of the some of the group 5 elements. Fluoride complexation, the trend shown here by theoretical calculations taking into consideration the relativistic effects is protactinium should have the highest complex formation with the fluoride ion, followed by niobium, followed by dubnium. Or niobium and dubnium, they may be having more or less same complex formation tendency, and tantalum should be having the least complexation with fluoride ion. So this was tested by extraction studies using Alicot 336, and from 6 molar chloride solution, this extraction followed the order protactinium, followed by niobium, followed by dubnium, followed by tantalum. So this confirms the theoretical calculation, and the KD values in the offline as well as online measurements for a particular condition is given here. You can see that the KD values around 1440 for protactinium, which is very high compared to that of niobium, that is 683, and dubnium values around 438, and which is again very large compared to that of tantalum, which is only 22 is the KD value observed. You can see that at this condition, these KD values are given. Now, another example I give, the aqueous chemistry of dubnium. So these studies are carried out using a mixture of hydrochloric acid and hydrofluoric acid using ARCA, and the extraction chromatography studies are carried out using trioctyl amine as the extractant. The extraction of niobium, tantalum, protactinium, which is a pseudo homologue, has been taken into consideration, and dubnium into tri-isooctyl amine from 12 molar HCl and 0.02 molar hydrofluoric acid, and also from 10 molar HCl studies were carried out. And in this case, dubnium was found to be extracted together with niobium, tantalum and protactinium. That means all 4 elements were extracted together. But after the first extraction step, the niobium and protactinium fraction was eluted with 4 molar HCl and 0.02 molar HF, and the tantalum fraction was eluted with 6 molar HNO3 and 0.0015 molar HF. And the observation was that 80% of the dubnium was with the niobium protactinium fraction, while only 12% was with the tantalum fraction. That suggests that dubnium is more or less following the similar chemistry of niobium and protactinium fraction. Now, to have a further distinction, 10 molar HCl containing 0.025 molar HF, protactinium was eluted first, and niobium was eluted with the 6 molar HNO3 containing 0.0015 molar HF. But then in this case, the distribution of dubnium was more or less equal with both these fractions. That is, around 25 alpha events were seen with the protactinium fraction and 27 with the niobium fraction. So that whatever trend is seen from this experiment, it doesn't match with what has been theoretically predicted. That means in this case, tantalum is having higher extraction, followed by niobium, followed by protactinium, and dubnium is somewhere also very close to that of protactinium. The last part in this series is the chemistry of seaborgium. Seaborgium is known to be member of the sixth group, that is molybdenum and tungsten, and it can also have a pseudo homologue of uranium. So when the experiment is carried out, for example, the cation exchange column studies using ARCA has been done, where the elution was done using 0.1 molar nitric acid and 0.5 millimolar hydrochloric acid together with the MOO42 minus and WO42 minus. These are eluted along with the seaborgium, suggesting that seaborgium also may be species like SgO42 minus. This type of species, anionic species, it may be forming, but this seaborgium does not follow the chemistry of uranium. This was very clearly proven. And another experiment was carried out in which 0.1 molar nitric acid was used as the eluent, and it suggested that seaborgium is different from molybdenum and tungsten also, and also based on the hydrolysis, it is considered entirely different as compared to molybdenum and tungsten. Molybdenum tungsten can form this neutral hydroxide species like MO2OH twice, but it was reported that seaborgium does not form this neutral type of species and always form a cationic species, even at higher pH values. Now, this is how I conclude the chemistry of this element 104, 105, and 106. To summarize, we see that these results from the recent studies, they justify the positioning of the trans-actinides starting with element 104 into the 7th period of the periodic table. And chemical studies are performed with rutherfordium, dubnium, and seaborgium both in aqueous as well as gas phase. The heavier transactinides gas phase chemistry also is reported, and all experimental results yield properties which place them these elements into their respective groups in the periodic table. A closer look reveals that their chemical properties cannot be predicted in a comparison with their lighter homologues. However, the modern relativistic molecular calculations show excellent agreement with the experimental data. Therefore, one can deduce the relativistic effects strongly influence the chemical properties of the transactinides. Subsequent experiments with element 118 has been also carried out, and recently these elements 119, 120, and 121 have been identified but need confirmation. This will start period 8 in the periodic table. And these studies are mostly carried out in the Lawrence Berkeley National Laboratory, USA, the Dubna lab in Russia, the GSI lab in Germany, and also RIKEN, Japan. Thank you.